Hi everyone, my name is Lap-Loi Chung from National Center for Research on Earthquake Engineering and from Departments of Civil Engineering, National Taiwan University, National Cheng Kung University. This is my name in Chinese, Zhong Li Lai. Welcome to the course Introduction to Seismic Design of Structures. This is lecture 2.1. The lecture is about simplified calculation of fundamental vibration period. From the previous lecture, we know that fundamental vibration period is a key factor for the determination of seismic design forces. And here are some terminology. Exterior column, in Chinese, 外柱. Interior column, 内柱. Stiffness matrix, 进度矩阵 mass matrix, 质量矩阵 and stiffness matrix and mass matrix are two key quantity for the determination of fundamental vibration period. And here's a static condensation, 静态浓缩. Through static condensation, we can reduce the number of degrees of freedom so that make the dynamic analysis much simple. And we consider one-story building first. Here's an assumption. We assume that the inflection point of the beam occurs at the mean point. That means that at the mean point, there's no moment. So that we can decompose the one-story building in the direction of the earthquake into exterior columns and interior columns. Here H is the height of the column. IC is the moment inertia of the column. L divided by 2 is the half of the span of the beam. IB is the moment of inertia of the beam. And for interior column, one beam is connected to the column. In the interior column, two beams are connected to the column. No matter it is exterior column or interior column, there are two degrees of freedom. One is delta. Delta is the lateral displacement at the joint, and theta is the rotation at the joint. And here we consider exterior column first. And from a structural theory, we can construct the stiffness matrix of the exterior column. And if we want to have a unit lateral displacement, that's the lateral force required at the joint. That's the moment required at the joint. If we would like to have a unit rotation at the joint, and this is the lateral force required, this is the moment required, so that we can construct a 2x2 stiffness matrix for exterior column. And under earthquake force, the rotation is very small, theta here, because the wavelength of earthquake is so long, so that for the size of the building is considerable small, so that under base acceleration or under earthquake, the rotational force is very small, and the rotation is very small, so that the rotational inertia force is very small, and also the external rotational force induced by earthquake is also very small, and external rotational force can be neglected. And with these two properties, and we consider the second equation, Ke21 times delta plus Ke22 times theta equal to 0. 0 here means that there's no rotational external force. That means that external rotational force is very small. And no acceleration here because the rotational inertia force is small enough to be neglected. And from this static equation, we can express theta in terms of delta. Theta equal to minus Ke21 divided by Ke22 times delta. Through static condensation, the degrees of freedom delta and theta are no longer independent. That means that they are dependent on each other. Okay, from this relationship between theta and delta, then we consider the second equation, the first equation, KE11 times delta plus KE12 times theta, and theta can be expressed in terms of delta, so that we can have KE11 minus KE12 times KE21 divided by KE22 delta. Here can be considered as the stiffness after static condensation. We call this KE. E means exterior column. K here means stiffness. And this is a scalar, or it can be considered as a general matrix, but the dimension is 1 by 1. And KE can be expressed as 12EIC divided by h cubed minus 6EIC divided by h squared, and then square again divided by 4EIC divided by h plus 6EIB divided by L. And after condensation, originally we have 2 degrees of freedom, but after condensation we have only 1 degree of freedom, so that the problem is easier to be solved. Okay, and then we move to interior column. And from interior column, we use the same method. We can construct the stiffness measures. And the dimension of the stiffness measures also 2 by 2. That means that if we want to have a unit lateral displacement, that's the lateral force required. That's the moment required. If we want to have unit rotation at the joint, that's the lateral force required. That's the moment required, so that we can construct the stiffness measures for the interior column. And with the same argument, under earthquake excitation, rotational inertial force is very small. They can be neglected. And under earthquake excitation, external rotational force is also very small. They can be neglected. So that we can consider the second equation, KI21 times delta plus KI22 times theta equal to 0. 0 here means that there's no external rotational force, and there's no acceleration here. That means that there's no external, no rotational inertial force, so that this one becomes a static equation. And from this static equation, we can express theta in terms of delta. And after static condensation, delta and theta are no longer independent. They are dependent on each other according to this relationship, so that we can reduce a 2 degree of freedom to a single degree of freedom structure. And with this relationship, we consider the first equation, Ki11 times delta plus Ki12 times theta, and theta can be expressed in terms of delta. And after the substitution, we can have this equation, Ki11 minus Ki12 times Ki21 divided by Ki22 delta. Therefore, the restoring force depends on delta only. And we consider this coefficient as Ki. I means the interior column. K is the stiffness. This one is 1 by 1. That means that it becomes a scalar equal to 12EIC divided by h cubed minus 6EIC divided by h squared, and then square again, divided by 4EIC divided by h plus 12EIB divided by L. That means that after static condensation, the number of degrees of freedom is reduced from 2, and here should be 2, and then divided into 1, and then it becomes a single degree of freedom structure. And if we consider all the column lines as springs arranged in series, therefore we can have the total or the stiffness of the whole structure, and is the summation of the stiffness of the exterior column and also the summation of the stiffness of interior column, so that we can have K is the stiffness of the structure, equal to summation Keij plus summation Kij. And M is the mass of the structure, and K is the stiffness of the structure. from the mass of the structure and the stiffness of the structure, we can compute the vibration period. T equal to 1 divided by 2 pi square root of m divided by k. And this one is the fundamental vibration period because there's only one period. And then we move to two-story building. And then with the same argument or the same assumption, the inflection point of the beam occur at the midpoint, so that we can decompose of all the column line along the earthquake direction into exterior columns and interior columns. No matter is exterior columns or interior columns, they have 4 degrees of freedom. They are delta roof. That's the roof, the lateral displacement at the roof. Delta 2F is the lateral displacement at the second floor. And theta roof is the rotation at the roof. Theta 2F is the rotation at the second floor. And H is the height of the column. IC is the moment of inertia of the column. L divided by 2 is the half of the span of the beam. IB is the moment inertia of the beam. And there are totally 4 degrees of freedom. And from structural theory, we can construct the stiffness matrix of exterior column, the exterior column here. And for this column means that if we would have a unit lateral displacement at the roof, that's the lateral force required at the roof, lateral force required at the second floor. That's the moment at the roof required. There's a moment required at the second floor. And if we would like to have a unit displacement, unit lateral displacement at the second floor, that's the lateral force required, that's the moment required at the roof, at the second floor, at the roof, at the second floor. So that we can construct, we have already constructed these two submatrix, KE11 and KE211. If we go further, if we would like to have a unit rotation at the roof, that's the lateral force required, that's the moment required. If we would like to have a unit rotation at the second floor, that's the lateral force required, that's the moment required. So that we can construct KE12, this summation. This submatrix, the dimension is 2 by 2. And also KE22, the dimension is also 2 by 2. So far we have already construct all the 4 submatrices, so that we are ready to have the stiffness matrix of the exterior column. And under the same argument, the rotational inertial force is small enough to be neglected, and also the external rotational force induced by earthquake is also small enough to be neglected. So that we can consider the second equation, KE21 times delta plus KE22 times theta equals to 0. 0 here means that there's no external rotational force. And there's no second derivative or no acceleration here because the rotational inertial force is negligible. So that this is a static equation, and from this static equation, we can express theta. Theta is 2 by 1 in terms of delta, and delta is a vector 2 by 1. And this process we call static condensation. That means that through static condensation, the degrees of freedom, delta and theta, are no longer independent. They are related to each other. Okay, with this relationship, and then we consider the first equation, KE11 times delta plus KE12 times theta. And because theta can be expressed in terms of delta, after the substitution of this equation into that equation, we can have KE11 minus KE12 times KE22 inverse times KE21 times delta. And then we consider this coefficient or this coefficient matrix as KE delta. delta means that the degrees of freedom of theta has already been condensed, so that we have a 2 by 2 matrix equal to KE11 minus KE12 times KE22 inverse times KE22. And then we move on to interior column. Also, from structural theory, we can construct those 4 submatrices. And this one is, if you would like to have a unilateral displacement at the roof, so that there's the lateral force required, there's the moment required at the roof, at the second floor, at the roof, at the second floor. And if we would like to have a unit lateral displacement at the second floor, that's the lateral forces required at the roof, at the second floor. And this is the moment required at the roof, at the second floor. So far we have already constructed these 2 matrices, KI11 and KI22. And then we are going to construct these 2 matrices. That means that if you would like to have a unit rotation at the roof, that's the lateral force required, that's the moment required. If we would like to have a unit rotation at the second floor, that's the lateral force required, that's the moment required. So that we can construct KI12 and KI22, and these 2 submatrices with dimension 2 by 2. Please notice that KI12 is the transpose of KI21. This one should be I. So far we can have already construct the submatrices for the stiffness matrix of interior column, Ki. And with the same argument, under earthquake, rotational inertial force is negligible. Under earthquake, external rotational force is also negligible. So that we can consider the first equation, the second equation, Ki21 times delta plus Ki22 times theta equal to 0. 0 here means that there's no external rotational force. There's no acceleration here because there's no rotational inertial force. And this equation becomes a static equation. And we can express theta in terms of delta. Theta equal to minus Ki22 inverse Ki minus Ki22 inverse times Ki21 times delta. And this process we call static condensation. Originally, delta and theta are independent. After static condensation, they are interrelated to each other. And with this relationship between theta and delta, and we consider the first equation, Ki11 times delta plus Ki12 times theta, and theta can be expressed in terms of delta. After substituting this relationship into this equation, we can have Ki11 minus Ki12 times Ki22 inverse times Ki21 times delta. And this one can be considered as the stiff matrix after static condensation. We call Ki delta because only displacement, lateral displacement, degrees of freedom are left. And Ki delta equal to Ki11 minus Ki12 times Ki22 inverse times Ki21. Originally, the dimension of the matrix is 4 by 4. But after static condensation, the matrix, the dimension of the matrix becomes 2 by 2. Okay, once we have the stiffness matrix for exterior column, and we have the stiffness matrix for interior column, and we consider all the columns are arranged in series. They consider as springs in series, so that the stiffness matrix of the whole structure equal to the summation of the stiffness matrix of exterior column plus the summation of the stiffness matrix of the interior column. Finally, we can have the stiffness matrix of the structure. And also we can construct the mass measures, M. M contains two elements. MRF is the mass of the roof. M2F is the mass of the second floor. And you can calculate it from the dimension of the members, from the dimension of the structure. And with mass measures and stiffness measures, we can conduct characteristic analysis. That's the determination of K minus lambda M equal to 0. And from this equation, we can have two roots. There's two eigenvalues. And then we pick up the lowest one and take the square root. We can have the omega 1. Omega 1 is the fundamental frequency. It's also the lowest frequency among the two frequencies. And from fundamental frequency, we can have the fundamental period, T1. T1 equal to 2 pi divided by omega 1. And T1 is the longest period. It's the longer period among the two periods. Because through characteristic analysis, we can have two eigenvalues. There's two frequencies and two periods. And the lower frequency is the fundamental frequency, and the longest period is the fundamental period. And from previous lecture, we know that the longer the period, the smaller the seismic force. In order to prevent the fundamental vibration period from being overestimated, so that the seismic force is underestimated, so that we can assign the upper bound for the fundamental vibration period. And from our seismic design code, we assign the upper bound for the fundamental period to be 1.4 times the fundamental period provided by the code. And here we assign it, we call it design fundamental period T, and T equal to the minimum of 1.4 T code and T dynamic. And T code is the approximated fundamental vibration period provided by seismic design codes as mentioned in the previous lecture. And T dynamic is the fundamental period from dynamic analysis, so that we can prevent the fundamental period from being overestimated. And also we can prevent the seismic force from being underestimated. And here are some references. The first one is published in 2011 by Ministry of Interior. That's the Seismic Design Codes of Building for Taiwan. This is in Chinese, and you can download this seismic design code from the website in the Ministry of Interior. The second one is stiffness measures. You can find out the information about stiffness measures from any textbook on structural theory, and mass measures from any textbook from structural dynamics. And static condensation, you can find it out from any textbook on structural theory. And characteristic analysis, you can find it out from any textbook on engineering mathematics. And here are some more references. There's the videos on the previous lecture, fundamental vibration period. This is the English version. This is the Chinese version. And also there are videos on simplified calculation of fundamental vibration period. The English one is the current one, and the Chinese one is stated here, and you are welcome to watch all the videos. And this lecture talk about simplified calculation of fundamental vibration period. And because of fundamental vibration period is a key factor for the determination of design seismic force. And in this lecture, the method for simplified calculation of fundamental vibration period is introduced. Although only two-story building and one-story building are mentioned in this lecture, but the method are already can be already extended to multiple degree of freedom structures. Thank you. That's all for this lecture. See you next time. Bye bye.